Okay, well, welcome everyone to another TCS Plus talk. We're very lucky to have Vera Traub today. She'll tell us about approximation algorithms for connectivity augmentation problems. And before we begin, let me just mention that, so 2 weeks from now, May 18, we'll have Thachapol Saranurak, who will talk about algorithms via reductions to max flow. And also let me thank the rest of the organizers. This includes Clement Canon, Rachel Cummings, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens-Davidowitz, Tomas Vidik, and David Weiss. So yeah, without further ado, I'll leave it to Vera. I also want to encourage people to keep their cameras on, give Vera some visual feedback. And yeah, feel free to ask any questions throughout the talk, and there'll also be questions and time to hang out after the talk. But all right, without further ado, Vera, please go ahead.
Yeah, okay, so welcome everyone. And yeah, so thanks Eric for the introduction, and thanks also to you and all the other organizers for organizing this and for inviting me here today. So in this talk today, I want to give you some overview of recent progress in the area of approximation algorithms for connectivity augmentation problems. And so let me start right away with giving you the definition of essentially the main problem that we will be talking about today. And this problem is called the weighted connectivity augmentation problem. In this problem, as an input, we are given some KH connected graph G with vertices and edges. So this is the graph that you can see here in black in this picture. This is some KH connected graph. In this example here, our graph is 3H connected, because in this graph, every cut has size at least 3. And then in addition to this black graph G, we are also given a set of X-Y edges. These are these dashed red edges in the picture. And I will call these X-Y edges in this talk always the links in order to distinguish them from the edges of the graph G. So these red dashed edges are the links. These are some X-Y edges. And these links come together with some non-negative weight, which is given by this weight function W here. Now, our goal in weighted connectivity augmentation is to increase the edge connectivity of this graph G by 1 unit. So we want to make this graph G k+1 edge connected by adding a subset of these links to the graph G. And we want to do that in the cheapest possible way, which means we want to choose a minimum weight set of links that we can add to our graph G in order to increase the edge connectivity by 1. So in order to make this graph k+1 edge connected. And so an equivalent way of phrasing this problem is to say that we would like to cover all the minimum cuts of our graph G by links. So for every cut here in this example, every cut of size k, or in this example, every cut of size 3, we will have to add one link that crosses this cut, and then we have a feasible solution. So this is the problem I want to talk about today mainly. And so let me start with some very important observation. Namely, we call that we want to essentially cover all the minimum cuts of our graph by links. And now there is some very well-known, or some kind of well-known theorem, some classic result by Dienitz and others, that says that the minimum cuts of a graph have a very particular structure, namely that they can be represented by a so-called Cactus graph. And so essentially what follows from this result, classic result here, is that we may assume, instead of looking at a general graph G, we may assume that the graph G that we are given at the beginning is a Cactus graph. So here in this picture, you see such a Cactus graph. And when I say here a Cactus graph, I just mean that every edge in our graph should be contained in exactly one cycle. So here you see this graph. This is a 2-edge connected graph, and every edge is contained in precisely one cycle. So you can also think of these cactus as sort of like a tree of cycles that stick together here at some vertices. And so in this example, we have this Cactus graph, and we would like to increase the edge connectivity of this cactus from 2 to 3 by adding a minimum weight set of links. And by this classic result, if we can solve that problem, that's equivalent to the problem of looking at a general graph. So in the rest of this talk, I will always assume that our graph is just such a cactus graph and we'll not have to look at general graphs anymore. Okay, so this was one important basic observation. And now I will in this talk, I will also talk about one important special case of the problem. And this is the so-called weighted tree augmentation problem. And this is the special, essentially a problem where our graph G for which we want to increase the edge connectivity, this graph is a tree. And this problem, this weighted tree augmentation problem is so important because actually if the edge connectivity of the graph we are starting with, so this was this K here, if this is an odd number, then it turns out that the weighted connectivity augmentation problem is actually equivalent to the weighted tree augmentation problem. And the reason is that if K is odd, the minimum cuts of the graph we are starting with have an even more special structure than this cactus structure, but actually it turns out that no two of these min cuts can cross in any way, and that is like the key fact that's behind this observation here, which is actually not very hard to prove, but I will not do that here in detail, that if the edge connectivity K is of this graph we're starting with is odd, then we may even assume that this graph we are starting with is a tree. So this is why this weighted tree augmentation problem is such an important special case of this general connectivity augmentation problem. So this gives us now like the following like 4 problems, which I just gave you an overview here again, which will be the problems I will talk about in this talk. The most general one is what I started with, this general weighted connectivity augmentation problem. We are given any graph and we have weights on the links here, these dashed edges, that we can add to our graph in order to increase the edge connectivity by 1. Here we may assume that our graph is a cactus. And then there are 2 important special cases. One is if the edge connectivity of our graph is odd, then we obtain this weighted tree augmentation problem where the graph we are starting with is a tree. And the other special case that is going to be of interest in this talk is just a special case where all the links that we want to add can add to our graph have the same weight. So basically we are just minimizing the number of links that we are adding instead of the weight. So this is the so-called unweighted connectivity augmentation problem, which is also called CAP. And then if I look at the unweighted case and where K is odd, then I get this unweighted tree augmentation problem, which is also known as TAP. So this is the most special case. So this TAP is a special case of all the other problems that we will be considering in this talk. So these are like the problems we will be concerned with. And so what is known about these problems? So in general, what we can say is that in terms of hardness, even the most special problem of these 4, namely TAP, this is APX hard, and this is APX hard even if we restrict to the special case where the trees that we are starting with have constant diameter. So already on trees of diameter 5, this tree augmentation problem is APX hard in the unweighted setting. So this was shown by Koutgamay and Lee in 2004. And then, so for this reason, we will be interested in discussing approximation algorithms. And so if we look at classic techniques that we can use for network design problems in general, which also includes this weighted connectivity augmentation problem, there are some very classic techniques like primal dual algorithms or the iterative rounding technique and so on. And these techniques, they give us a 2 approximation algorithm for a very wide class of network design problems. So this includes this weighted connectivity augmentation problems, but also way more general network design problems. So in some sense, these 2 approximation is sort of the baseline that we'll be comparing to. With 2 approximation is the thing we can always get using the classic techniques. But somehow, even though we know like these classic techniques are now known for quite a while and we can get 2 approximations for very general problems, there are many very basic special cases for which we don't have no idea how to get better than this 2. So even if we look at very particular problems, in many cases we don't know how to beat these general techniques here. So this is sort of like the main question we're always asking. That's kind of important here is, can we get better in two approximations? So 2 is what we can always get. Good. So in the rest of this talk, I will give you an overview of what we know about better in two approximations. I will first talk about the unweighted settings, so unweighted tree and connectivity augmentation. This part will be rather brief, and then I will just give you some very high level overview of the techniques that people use here. And then I will, in this second part, I will focus a bit more and go into a little bit more detail on the weighted problem. But let's get started with unweighted connectivity augmentation. So what is known there, so in particular, like the unweighted tree augmentation problem has been heavily studied, and there we know better than two approximations for about 20 years now, where the currently best known approximation ratio is 1.393, which we obtained in some recent joint work with Federica Cecchetto and Rico Zanclusen, but you can see here this was building on a long list of results, of prior results. So this problem has been very intensively studied, this unweighted tree augmentation problem. So even though this TAP problem here was studied so heavily, it took quite a while until we got the first better in two approximation also for the connectivity augmentation problem. So here, the first better in two approximation was only given in 2020 by Burkhard Guandoni and Jabal Meli, and they obtained a 1.91 approximation. And recently, we could also improve this to 1.393 approximation. So this is actually matching. You see here, that's the same approximation ratio as for the unweighted tree augmentation problem. So here we could actually generalize to get the methods from tree augmentation to get the same result also for connectivity augmentation. So what is interesting to note here maybe about the techniques for this unweighted connectivity augmentation problem is like the techniques used in these two papers here are actually very different. So the first one by Burkhard Guandoni and Jabal Meli works via some reduction to some node-weighted standard tree problem, whereas the second approach here is building on the techniques from TAP. So this paper is like strengthening and generalizing the techniques that were previously known from TAP, and is building on these papers on a line of work started by Adjishvili in 2018, and is generalizing these techniques from there. So now in the following, I will give you some brief, like one slide overview for each of these two techniques, because I feel they are both like interesting. Also, this first one provides some very interesting connection to this node weighted standard tree, and then afterwards I will move on to the weighted setting. So let's start with this 1.91 approximation for CAP. And so what this reduction is doing, it actually first uses that there was some reduction which was previously known by Bazavarayu and others from 2014. They actually were interested in fixed parameter tractable algorithms for connectivity augmentation. And they gave some non-approximation preserving, but some reduction of CAP or WCAP to some node-weighted standard tree problem with some particular structure. So what is node-weighted standard tree? So node-weighted standard tree, we are given some graph here. So you can see here in the bottom some example. We have some subset of the vertices. These are terminals, which we call terminals. These are these green squares here. And then our goal is to find like a standard tree, as you can see here in orange, that connects all the terminals together. And the important thing here, why this is called node weighted, is that we have weights on the nodes. So we actually pay here for these orange vertices that we used here in our standard tree. In general, this node weighted standard tree problem, this is at least a set cover hard. So we cannot hope for any like good approximation algorithms there. But these node weighted standard tree problems that arise here from this reduction, they have a very particular structure. And this is something that then Burkhard Guandoni and Jabal Meli used, and they showed that for these particular standard tree, node weighted standard tree instances, they could adapt some algorithm for the edge weighted standard tree and use a similar kind of analysis to get for these node weighted standard tree instances with this particular structure, also a good approximation algorithm, and this way obtained their better than 2 approximation for CAP. So this was on a high level the technique that they used. Now the second better than 2 approximation for CAP that we know, which is some joint work with Federica Cecchetto and Rico Zanclusa, that follows more like the approaches that led to the commonly best known approximation guarantees also for the tree augmentation problem. And so this works essentially in 3 steps. So the first step is that we reduce the problem to instances with a very particular structure, and namely to so-called k-wide instances for constant k. So what is a k-wide instance? So an instance is called k-wide if there exists one particular vertex, which I will call the center in the following. This is this green vertex here on top. And then from the center here, we call that we have a cactus graph. There are some like subcacti that are sort of hanging off the center. So here we have these 3 subcacti hanging off the center. And then I say that an instance is k-wide if in every sub-instance here hanging off the center, I have at most k terminals, where a terminal is simply a vertex of degree 2. So the way you should think of terminals are you should think of terminals as sort of the analog of leaves in a tree. So a terminal in a cactus is sort of the analog of a leaf in a tree. So these are here vertices of degree 2. And here, this instance in this example, for example, is 5 wide because in each of these subcacti hanging off the center, I have at most 5 of these terminals. And what this first reduction here says is that if we have an alpha approximation algorithm for k-wide instances, then I get for the general problem, an approximation algorithm with approximation guarantee alpha plus something in the order of 1 over square root k. So this means if I choose k, some large enough constant, I get some, at the cost of losing some arbitrary small epsilon, I also approximate the general problem. So this allows us to focus on instance of k-wide instances for constant k. That's the first main ingredient of the algorithm. And then in the second step, we give two algorithms, these which we call the so-called backbone procedures for these k-wide instances. And the approximation guarantees of these algorithms depend on the types of links that appear in an optimum solution. And so what do I mean by this? So we kind of partition the links into 2 groups. The one links, these are these blue links here, is what we call the in links. These are links that have both endpoints in the same subcactus hanging off the center. So here the blue links here are those in the first subcactus hanging off, and here were some more blue links which are completely inside and the subcactus hanging off the center. And then the cross links, these are the red links. These are the ones that go between the 2 different subcacti hanging off the center. And then we obtain 2 approximation algorithms where the first one has a guarantee that is very good if we have many in links in our solution, in our optimum solution, and loses a factor 2 on the cross links. And the other algorithm has a sort of complementary guarantee, namely it loses a factor 2 on the in links, but loses nothing on the cross links. And now you can already see if I take the better of the results of these 2 algorithms, that will give me immediately a 3/2 approximation. So if I take just the average of the 2 guarantees. This is not quite as good as what I promised you. So this, actually the algorithm has a third ingredient, which is what we call the so-called stack analysis. This is essentially a strengthening of this algorithm here, of this algorithm A here that has a good guarantee. That has a good guarantee if we have many in links, and combining these ingredients together gives then in the end leads to this 1.393 approximation. So this is,
I'm a bit confused with the definition of k-wide instances. So if you take k to be larger, then I guess the requirement is weaker.
Yes.
But you have better approximation.
If we take k larger, then we get a better approximation. So we need to choose, like, in the end we choose k large enough, but we choose it constant. So we need this to be constant for our later algorithms to have like still polynomial runtime. So the runtime of these backbone procedures later on will depend on k. So k can appear in the exponent. So that's why we need k to be constant. And then we just choose k large enough to get make such that this term here, this order of 1 over square root k term becomes
so the runtime also
epsilon.
K, so you don't want a
Yeah.
lot Vera.
Exactly. So the runtime of the later algorithms, that's why they work only for constant k, because the k there will come into the runtime.
Oh, thank you.
Okay, good. Okay, so this was some brief overview of like the kind of techniques that are like used on a high level in this unweighted for these unweighted connectivity augmentation problems. And in the rest of the talk, I will now focus on going into a bit more detail of what we know about these and the algorithms we found there for weighted connectivity augmentation problems. So what is known for weighted connectivity augmentation problems? Actually, for the general weighted connectivity augmentation problem, the current best approximation ratio is still 2. So it's still open to beat this factor of 2 in the setting for the general weighted connectivity augmentation problem. But we recently made progress for the weighted tree augmentation problem. So this special case there. For weighted tree augmentation problem, also until very recently, not much was known. So one important result there is that in 2011, Cohen and Nutov showed that if the tree in our weighted tree augmentation problem has constant diameter, then we can obtain a 1 plus ln2 approximation. So this is a little bit the guarantee here. 1 plus ln2 is a bit less than 1.7. But this was only for trees of constant diameter. And then only like last year, in some joint work with Ricots and Clusen, we managed to generalize this result by Cohen and Nutov to general instances of weighted tree augmentation. And there we obtained an approximation guarantee of 1 plus ln2 plus epsilon. So again, this is a bit less than 1.7. And then in some follow-up work, which is again some joint work with Ricots and Clusen, we could improve this to as we have plus epsilon approximation. So yeah, in the rest of this talk, I will explain you how this 1 plus ln2 plus epsilon approximation works, and then I will also give you some brief idea of how we can improve this to 3½ plus epsilon here. Okay, but before we get actually to this better than 2 approximation there, let me as a warm-up first explain you a simple way of how we can actually even get just a 2 approximation for WTAP. And so to start with, let me just remind you briefly of the definition, WTAP. So again, we were given a tree G here with vertices and edges that you can see in black. And then we have these dashed orange edges, which are the links. These are these extra edges that come with some non-negative weight. And our goal is to find the minimum weight subset of the links that we can add to our tree G to make it tree-edge connected. So in this example, a feasible solution could consist, for example, of those 4 links here. Now, it is when we want to design now algorithms for weighted tree augmentation, it is often useful to view this problem from a slightly different perspective, namely to view WTAP, so the weighted tree augmentation problem, as a kind of a covering problem. So remember that our goal is to essentially cover all of the min cuts of our tree G here by links. And so essentially, I want to cover all the cuts that contain just a single edge of my tree G by links. So this allows me to view this weighted tree augmentation problem as a covering problem, where I can say that my links should cover all the 1 cuts of my tree, which is simply correspond to the edges of my tree by links. And the way I do this, I will say a link L, like this blue link L here. Simply, I say this link covers all the edges on the path PL between its endpoints. So on this green path here. And if I do this, then I can formulate the weighted tree augmentation problem equivalently as follows. I can just say, I want to cover all the edges of my tree G by links, where every link covers the edges on the path between its endpoints. And that's an equivalent formulation of weighted tree augmentation. And that's much more useful to look at the problem in this way when we want to design algorithms for it. Good. So that's was sort of, yeah, basic observation. Now, how can we get a true approximation for WTAP? So what we will do is we start by first picking an arbitrary root vertex of our tree here. And then in the second step, I will split every link into two so-called uplinks that each have the same weight as the original link and together cover the same edges as the original link. So let me show you what I mean by this. So first of all, what is an uplink? So an uplink is simply a link where one endpoint of the link is an ancestor of the other endpoint in this tree, 2G here. So all the links here in this white picture are uplinks because for every link I have the property that there is like an upper endpoint that is like an ancestor of the lower endpoint of the link in this tree here. So all of them are sort of pointing upwards towards the root. These are uplinks. And now it turns out you can split every link into two uplinks that together cover exactly the same links as the original edges, same edges as the original link. For example, if I look at these two brown links here, these two uplinks here, they cover together the same edges that were also covered by the original brown link here. I simply do this by splitting the link in such a way that from both endpoints, I have a link going to the least common ancestor of the two endpoints of the original link. So here, for example, this green link, the least common ancestor is this vertex. So I split this green link into these two uplinks. I just replace it by them, and each of them gets the same weight as the original link. In this way, of course, if I do this in my instance, then the weight of an optimum solution increased at most by a factor 2. I can always buy the two new uplinks instead of the original link. Now, why have I done the splitting? So the reason is that if my instance now has only uplinks, and the nice thing is that once in a weighted tree augmentation instance, if my instance contains only uplinks, then it actually becomes polynomial time solvable. So if I have an instance with only uplinks, I can solve it optimally in polynomial time. And there are a couple of different ways of doing this. One way would be to write down the natural LP, linear programming relaxation, and it turns out that this relaxation is integral. Another way to do this would be to use some dynamic programming algorithm that is going bottom up over the tree. And also with this way, one could compute an optimal solution that contains only uplinks. And then if I have my optimal uplink solution, I can replace every link with the uplink with the original link from which it arose in my instance. And this gives me my true approximation. So this is a very simple way of getting a true approximation. And this will also be useful now in the following when we are trying to obtain these better than true approximations for weighted tree augmentation. Okay, so let's get to this. Let's see how can we get better. And this is now some joint work with Rico's inclusion. And the algorithm we have here is a so-called relative greedy algorithm. And so with the relative greedy algorithm, such algorithms have also been used previously for other problems, in particular, for example, for the Steiner tree problem. And the general idea of such relative greedy algorithms is that we start with some rather weak but highly structured approximate solution. So in this case, we will start with some true approximation that is going to be highly structured. And then in the course of the algorithm, we sort of replace parts of the starting solution by some better components, and this way improve the approximation guarantee of our solution. So let's make this more concrete. In the case of weighted tree augmentation, the solution we start with is the following. So in order to obtain the starting solution, we first compute an optimal uplink solution, which is a true approximation. So this just means we just apply this true approximation algorithm that I just showed you like a minute ago. And this already has some quite nice structure. Namely, we know that we only have uplinks in our solution. Now what we will do is we will make this solution even more structured. Namely, we will make sure that every edge in our tree is covered only by exactly one of these uplinks. So we know that we have a feasible solution here on the left, so every edge will be covered by at least one of the uplinks, and we want to make sure that every edge is covered by exactly one of the uplinks. So here in the left, for example, this brown edge here is covered by both of the two green links. And in order to avoid this, what we'll do is we'll shorten one of the green uplinks, namely by just moving here this endpoint of this green uplink downwards along this brown edge. So here we've shortened this left green endpoint. So the reason why we can do this is we are always allowed to shorten links just because we are just making the link weaker. So we are just replacing it by some link that covers less than what the original link covered. This is always fine. We are just making our life harder by doing that. And it turns out that if we have only uplinks in our solution, you can always apply shortening operations such that at the end, every edge is actually covered by exactly one of the links. So this way, we obtain the starting solution for our relative greedy algorithm, which is this highly structured solution. Namely, we have a 2 approximation, and then we have this structure that we have only uplinks, and every edge is covered by exactly one of the uplinks. So this is quite a lot of structure, and this is something we can use in the following. And now let's come to the actual relative greedy algorithm. So we now want to improve on the starting solution. In this relative greedy algorithm, we will always maintain a feasible solution to our weighted tree augmentation problem. And we will always write this as U union F, where U will always contain only uplinks and F can contain arbitrary links. Initially, we set U to be this highly structured starting solution, which is the 2 approximation, and we just set F to be the empty set. And then in the course of the algorithm, what we will do is, as long as the weight of our solution decreases, so as long as we are making progress and our solution is getting cheaper, we'll do the following. We will select some component C and think of a component for the moment just as some subset of the links. So for example, these 2 green links here on the right. And then we'll add this component to our solution. Because this component can contain arbitrary links, we'll add it to F, this set F here. Of course, now if we add the set F to our solution, add this component C to our solution, then there are some other links, some uplinks in U that might become redundant. We don't need them anymore. So in this example here, these 2 red links become redundant. We can remove them from our solution. And this is the set. What we remove here is actually the set which we denote here by the drop of the component. This is the set of all those uplinks in U that cover only stuff that is also covered by my component C. So these are links that I can clearly safely drop from my solution when I add the component C. So I'll just remove that from my solution. And then I iterate this as long as the weight of my solution decreases, and in the end I return my solution. So that's the basic idea. Of course, one crucial question here is, how do I select this component C here? How do I select this link set to add here? And the way we do this is we choose the component C such that it minimizes the ratio between the weight of my component, so the weight of what I add to my solution, divided by the weight of the drop, so the weight of what I remove from my solution. And I will choose my component C among some restricted class of components. And within this class, I will minimize the weight of the components, so the weight of what I add, divided by the weight of the drop, so the weight of what I remove. So in some sense, I'm minimizing the factor by which the stuff that I replace becomes cheaper when I add my component. And so this is generally the idea behind such relative greedy algorithms. And a key question here is, of course, how do I choose this restricted class of components here that I can choose from? And let's first think a little bit about what kind of properties should this class of component have. So the first thing is actually, which is maybe the most obvious thing, is that we actually should be able to efficiently find the best component to pick next. So we should define our class of components in such a way that we are able to efficiently find the best component to pick next. So we should be able to find this and solve this minimization problem. If we have this, then we are able to efficiently implement our relative greedy algorithm. Now, of course, we also want our relative greedy algorithm to be good. And what we need for this is essentially that we make at least a little bit of progress. So we call it initially, we start with a 2 approximation. Our main goal is to beat factor 2. So at least what we need is that if initially the weight of U is only a 2 approximation, so if it's much larger than the weight of an optimum solution, then there should exist a component that we can use to make progress. So where what we add is much cheaper than what we can draw from our solution. And turns out if you have the second property, then you can guarantee that until you've replaced a large fraction of the uplinks, a significant fraction of the uplinks that you had initially, as long as until this happens, then we are still kind of making significant progress and making things cheaper by a lot. So if we have property B, then we already get a better into approximation. Now, what is a good choice for the class of components? So a very natural choice, and this is actually what Cohen and Nutter have used for the special case of constant diameter trees, is to just allow as components constant size link sets. The good thing about this is property A in this case is trivial. We can just enumerate over all possible link sets. The problem is property B actually doesn't hold anymore in the general setting of weighted tree augmentation. So we actually have a counterexample that shows that if we just work with constant size link sets, relative greedy algorithm for WTAP doesn't have an approximation guarantee of better than 2. So constant size link sets are not general enough. Now another good candidate, at least for a sanity check, is to allow arbitrary link sets. If we have arbitrary link sets, the second property, property B, becomes trivial because as a component, we could always take the optimum solution. Then if I add the optimum solution, then I can drop everything from U. So this means the drop here will be just the whole set U. So if the weight of U is still much larger than opt, then I can just replace everything of U by opt, and this will be a good exchange. I will make progress by that. But of course, it's elusive that we will actually find that link sets, this optimum solution. So we have no idea how we should be able to efficiently find the best component, and most likely it's not going to be easy then to solve the weighted tree augmentation problem that we started with in the beginning. So now the question is there something in between? Is there a good class of components, something that is like a class of components should have enough structures such that we can efficiently find the best component that we can pick next? But on the other hand, it should also be general enough, this class of components, and not just contain constant size link sets, such that we can actually guarantee the existence of an improving component whenever we need it. And it turns out that there actually is such a class of components. Of course, otherwise I wouldn't be telling you all of this. And this is what we call these k-thin link sets. So let me explain you what the definition of these k-thin link sets are. So we call a set of links k-thin if for every vertex v, there are at most k links in my component such that v lies on this path PL between the endpoints of the link L. So let me explain you this once again here. Let's go through this example here on the right. I claim that these 3 orange links here form a too-thin component. So this is a too-thin link set. And what you need to do in order to check this by the definition is we need to look at every vertex V here, at the vertex V in our tree. And then we look at the path PL, so this green path between the endpoints of such a link in my component. And here's the green path PL connecting the endpoints of this link here. And here V lies on this path. And V also lies on the green path between the endpoints of this link here. But it doesn't lie on the green path between the endpoints of this third link here. So V is lying on at most 2 of these 3 green paths. PL between endpoints of link in my component. This is why I call my component like too thin, because this property actually holds for every vertex in this tree here. So this is the definition of k-thin components. It turns out that with this definition of k-thin components, it's actually possible to efficiently solve this minimization problem here. So we have this property A. This can be done with some fairly standard dynamic program going bottom up over the tree. And actually, this definition of k-thinness is made in precisely such a way that if you apply some standard dynamic program going bottom up over this tree here, that this has polynomial runtime for constant k. So we'll later just choose as components in our algorithm will allow k-thin components for constant k. So this is actually not too hard to see. I won't go over details of this, but this is like a standard dynamic program, this property A. the interesting part of the analysis is actually to show the second property B. So to show that there always exists a good component that we can use to make progress whenever we need it. And in order to show this, we show a certain decomposition theorem. And what this decomposition theorem says is that it says that we can always partition, if we look at some optimum solution to our problem, to Unweighted Tree augmentation problem, then there always exists a partition of this optimal solution into components such that we get some lower bound on the size of the drops of these components. So let's just think a little bit about what this lower bound here does. So, like in some sense, the best thing that we can hope for if we partition our optimal solution into components and look at the drops there of the size of the drops of these components, the best thing that we could hope for in general is essentially that every uplink in U is contained in one of these drop sets. And in that case, I could say that the sum of the weights of these drops would be lower bounded by the weight of the whole set U. That would be the case if every uplink, each of these blue links here in my uplink solution U here is contained in one of the drop sets of these components. And what this decomposition theorem here tells us is essentially we can almost achieve this best possible lower bound up to this 1 minus epsilon factor here. And now actually, once you have this decomposition theorem, it's not so hard to prove that our relative greedy algorithm has the desired properties, namely that improving components exist. So the way you do this is essentially you do some averaging argument over the components in this partition C. So we know that these components in C here are cheap altogether because they form a partition of opt. And we also know that if we sum over all components, the drops are large. So this means there has to be, by some averaging argument, there has to be one component where the weight is relatively small compared to the drop, because the total weight is small. That's just the weight of up, and total weight of the drops is large by the decomposition theorem. And there's like essentially by some averaging argument, you get the desired properties from this decomposition theorem. So this is like proving this decomposition theorem is really the core of the analysis. I will not get into this here today. So this was just some rough overview of how the analysis roughly works. And now I would like to use the remaining minutes to just say a few words about how we can improve this relative greedy algorithm and to obtain 3/2 plus epsilon approximation, which is again some joint work with Rickert and Clusen. And so here, the basic idea is that, so recall that in the relative greedy algorithm, essentially we started with this uplink solution, and then we added component and removed some of these uplinks that we had. But we always only replace uplinks from the starting solution. It could also be maybe we add some component later on, and then some links that we added in some previous iteration, maybe they also become redundant. In the relative greedy algorithm, we didn't remove them. We didn't take any advantage of this. And now the idea is to improve on this. Maybe we can also take advantage of by potentially removing links that we added in some early iteration of the algorithm. The difficulty here is that if links that we added in some early iteration, they might be not uplinks. So the uplinks in our starting solution, we always only had uplinks. But links we added later on in some early iteration, they are potentially not uplinks. And the problem is we don't really know how to analyze when we can remove those uplinks, because our decomposition theorem only applies allows us to analyze when we can remove uplinks, when we can drop those. And the general idea to get around this problem is that if we have such a link L here that we added in some early iteration, we think of this link as being split into two uplinks. This is what you can see on the right. This is just, we split it just the same way as we did it in the beginning in our true approximation algorithm, for the weighted tree augmentation problem. I will call these two links here the witness set of the link, and I just think of these two uplinks here as sort of the left and the right half of my original link L here. And I just do this essentially. Well, yeah, just I think of this link as being split in these two halves, and then the idea is that using my decomposition theorem, I kind of can analyze when I can remove the left or the right half of my link from my solution. And as soon as I know that as soon as I was able to drop both the left and right half from my solution, then I can also actually remove the original link L. So as soon as if I know I don't need the left and I don't need the right half anymore, then I don't need the link L anymore. So this is like the idea behind for a key idea for making progress and improving on this relative greedy algorithm, and how we can handle also removing general links, not just uplinks. And what is important here is that if we want to make this kind of algorithm work, it's important that we somehow reward partial progress so that we can already see some progress in our algorithm once we're only able to drop one of the two halves of our link, even if we couldn't yet remove the whole link from our solution. And I will just give you a one slide overview of how the actual algorithm looks like. Yeah.
Please go back to the previous slide.
Sure.
So do you need to assume that every vertex is covered by exactly one uplink after you do the splitting?
Like here on the right.
Yeah, because previously you in your previous algorithm, you need to assume that.
I see. Yeah. Very good point. Let me just comment on this on the next slide. Okay. So when I come to the algorithm, so what we do there in the algorithm is we will always maintain two solutions. The first one is just a general solution to our weighted tree augmentation problem. Think of this as being actually our current solution that we have at hand. And then we also maintain a second solution, which consists only of uplinks. In this uplink solution, think of this this is like the uplink solution corresponding to the one on the left. And we obtain this by first of all splitting every link into two uplinks. This gives us these witness sets. But then, and this is just exactly what we do then also, is exactly the point that was just pointed out as a question. It was a very good question. We will shorten the uplinks here on the right in such a way such that such that every edge is covered by exactly one link. And then actually, like now these two red links here, they will form the witness set of the link on the left. But this is really just a technicality that's important to apply this decomposition theorem. You can still sort of think of these two links here, red links here, as the left and the right half of this link here, and on the left picture. This is more like, yeah, that's not super important for the algorithm, but it's actually a key detail, an important detail if you want to apply the decomposition theorem later. That was a very good point. So then what the algorithm does is we essentially do local search steps, where a local search step does the following. We add some component C to our current solution. Then this is like, so current solution meaning we add it to our component, to our solution here on the left. And then we will also add the corresponding uplinks. So the ones that we get by splitting every link into two uplinks here on the right. And then once we added these uplinks here, added these components and the corresponding uplinks to our two solutions, we remove in our uplink solution here the drop. So the good thing here is that this procedure here of adding and removing things on the right is something we can analyze very well using our decomposition theorem. Of course, actually, after removing the drop, we will also shorten links here such that we always make sure that our uplink solution has this property that every edge is covered by exactly one link. But again, that's a technicality. And then so on the right side, we will just remove links as we've done it before in the relative greedy algorithm. And on the left side, we will remove a link whenever its witness set becomes empty. So whenever it's both its left and its right half in the right solution, whenever they both became removed, then we can also remove a link on the left side. And actually the solution that we return in the end is the solution F that we have at that moment in our local search procedure. So what the algorithm then does is it does some local search steps just as long as some carefully chosen potential function decreases. You need to choose this potential function in such a way that the algorithm also sees some progress, even if we just remove one of the uplinks here on the right, and even if our actual solution F maybe didn't become cheaper right away, but maybe we just made some progress by removing some of the uplinks here on the right. This doesn't necessarily mean that F becomes cheaper. So this is why as an objective function in the local search, we cannot simply use the weight of our solution F, but we have to use some carefully chosen potential. Good. So this was some overview of admittedly some high level overview of how this local search thing works. And now with this, I will come to some conclusions. So first, before summarizing, I would briefly mention two results that are related to what I told you about today. So the first result I want to mention is some joint work with Fabrizio Grandoni and Augmentation, and this is on a related problem called the forest augmentation problem. In this problem, we are given some arbitrary graph G, and again, some set of links L, which you can see here in orange. And now our goal is essentially to increase the edge connectivity. So to augment this graph G into a two-edge connected graph. So we would like to add links to our graph G such that the resulting graph is two-edge connected. And I said we can start here with an arbitrary graph, but actually one can assume without loss of generality that this graph is the forest, and that's why the problem is called forest augmentation. So this is also a network design problem. And note that here we are actually talking about the unweighted version. So we just want to find a minimal set of links that we can add to G to obtain a two-edge connected graph. And here we actually used this relative greedy algorithm that we developed for weighted tree augmentation, and we applied this relative greedy algorithm in essentially a black box way. And this was useful to obtain the first better than 2 approximation for this forest augmentation problem, even though there we only got slightly below the factor 2. So this is one application of these techniques that I presented you today. And then another result I wanted to mention is an application of this technique by Burkhard Grandoni and Jabal Ameli. This was this reduction of CAP, so connectivity augmentation, to this node-weighted synergy problem. And this kind of techniques have been recently used by Angelidakis, Denisic, and Sanita to give better than 2, like a 1.892 approximation for the problem of augmenting the node connectivity of an arbitrary graph from 1 to 2. So this is a result about node connectivity, but not edge connectivity. So this is following these techniques of this kind of reduction to a node-weighted synergy problem. So these are two related problems where techniques from this talk were useful. So I wanted to briefly mention this. And now here, let me once stop here by summarizing like the state of the art for these 4 problems that I've been mainly talking about today. So for weighted connectivity augmentation, we still have like the best known approximation guarantee is a 2 approximation. So it's still open whether we can beat this. Then for weighted tree augmentation, the best is this 3.5 plus epsilon approximation. That was this local search algorithm that I showed you in the end, which was improving on this relative greedy algorithm. And then in the unweighted setting for tree and connectivity augmentation is actually just one algorithm. We get the same approximation guarantee for both problems, which is 1.393. This number might look a bit strange here, and it's also for sure not like the right answer. It's also like this algorithm that I've briefly shown you for connectivity augmentation is for sure not tight. So it's not clear yet.
I'm not sure if I'm still seeing slide 26.
Okay. Let me just.
There we go. Okay.
Okay. Good. Okay. Yeah. Sorry. Yeah. Okay. So here's just like again a summary of these problems here, and so for connectivity augmentation, tree augmentation, the unweighted problem, we have the 1.393, but this is not tight, and it's, so this is open to find like maybe a tight analysis of the algorithm we currently have, or maybe a completely different algorithm with a better guarantee. And so then in terms of open questions, I already mentioned beating of cost factor 2 for weighted connectivity augmentation is open. And then another interesting problem I would like to mention here is to beat a factor 2 for the minimum weight to its connected spanning subgraph problem. So this problem was just you're given a graph G with non-negative edge rates, and you want to find a subgraph of minimum weight, which is 2-edge connected. This generalizes both the weighted tree augmentation problem, but also this forest augmentation problem that I mentioned on the previous slide. And so for this, also we have a true approximation by these methods for network design, but beating this approximation ratio is 2 is open. So that's also a very natural problem to look at next in this line of research here. And yeah, with that, I would like to conclude here. So thanks a lot for listening, and I'm happy to take further questions.
Thanks, Vera. So yeah, I mean, are there any questions? Feel free to unmute yourself and ask. So I have one question in the decomposition theorem. Why is 1.5? Why do you get stuck in 1.5? But you can for the weighted problem, but for the unweighted, you can get 1.3, or you can improve.
Like you're asking why the techniques for the unweighted thing don't extend, or yeah, maybe like
I see.
for the like so what happens like for the unweighted problem, we can improve, because so for the unweighted problem we use like for this 1.393 we use like this kind of approach with these 3 steps. And the main problem is like here, so these later steps, these backbone procedures and so on, they all work also for the weighted setting. Mm-hmm. The problem is that this reduction to these particular instances, these k-weight instances, this essentially breaks completely once we have weights. So actually like they still kind of work if we have like bounded weights, so if weights are bounded by like some constant or something like this, you can even get to things like log n or something like that. But then for arbitrary weights, this reduction to k-weight instances just breaks completely, and then the whole approach doesn't work anymore. And that's why like for the weighted setting, so for like we don't have any idea of how to generalize these techniques from the unweighted one to the weighted setting, and essentially it's using completely different set of techniques at the moment. But yeah, we have just, the main problem is this reduction to k-weight instances.
I see. Okay, thanks. Okay, so I'll stop the recording now.